Hi everyone, thank you for watching this presentation. My name is Teguh and I'll present our work on learning constraint distributions of robot configurations with generative adversarial network. In robotics, we often work with the configuration space of the robot. So this space may consist of the joint angles or also the base position of the robot in the case of a floating base robot. But often the configurations are also subject to a lot of constraints which define a manifold within the space. This manifold is basically a subset of the whole space, and it may have a fewer number of dimensions. And we want to be able to sample effectively from this constraint manifold. An example is a humanoid robot that is subject to different constraints. For example, the center of mass has to be within the super polygon, and the foot has to be on the ground, while sometimes the end effector orientation has to be along certain direction. For example, while holding a glass, the end effector has to be in vertical direction. So when do we want to sample from this manifold? An example is inverse kinematics, where we want to retrieve configurations that are in this manifold, satisfying the constraints, but also achieve the end effector task. Another example is sampling-based constraint motion planning. So this is usually based on the standard RT. In the standard RT, we want to build a tree of configurations in this configuration space. So the tree starts from the initial configurations and it extends towards the goal configuration. When the configurations have a lot of constraints, on the other hand, we need to build the tree on this constraint manifold. So we need to be able to generate configurations that are from this manifold. So how can we sample effectively from this manifold? The standard approach is to use uniform sampling that sample from this configuration space so that the configurations are not satisfying the constraints. Then we perform optimization to project the configurations on the constraint manifold. So while this approach works quite effectively in practice, it requires a lot of number of iterations, in the order of 10 to 20 number of iterations. So in our proposed approach, we propose to use GAN to learn the distribution of this manifold, so that we can use GAN to sample configurations that are already close to the constraint manifold. Not exactly, but quite close. Then we do also optimization to project the configuration to the manifold. In practice, this optimization step will have much fewer number of iterations as compared to the standard approach, because we start from the good initial configurations. And it results in faster computation and also higher success rate, because we start from good initial configurations. This is what it looks like. In uniform sampling, we sample random configurations and then we project it to the manifold. While in GAN sampling, the initial configurations are already very close to the manifold. In fact, the projection step cannot be seen visually here because the change is very small. Now, how do we train GAN to learn the distribution of robot configurations? First, we'll look at the standard structure of GAN. GAN usually consists of two major components, the generator and the discriminator. Both of them are usually neural networks. And the generator task is to provide good sample. In this case, a sample corresponds to a good configuration. And the discriminator task is to discern whether the configuration is a good one or not. And it does that by learning from the data set. So we assume that there is a data set of good configurations, and we give both the configuration from the data set and configuration from the generator to the discriminator. Discriminator assumes that the configuration from the generator is a bad one and the dataset configurations are the good ones. So given a configuration, it has to determine whether it comes from the generator or from the dataset. While the generator, on the other hand, is trained to deceive the discriminator into thinking that the configuration it produces come from the dataset instead of from the generator. So it's a competitive game between the two, where one tries to deceive the other and the other one tries to be smart in discriminating. And by the end of the training, we hope that the discriminator will learn the good feature of good configurations and the generator will be able to provide configurations that are very similar to the dataset and will be considered as good configuration by the discriminator. Now the problem of applying this standard structure to our problem is that it can require long training time and it may require a lot of data. While actually in robotics we have a lot of prior knowledge that of what constitutes good configurations. So instead of just relying on the discriminator, we can also use this prior knowledge in order to help the training of the generator. So we will see this later. This is our proposed structure of GAN with several modifications. First, we introduce the target and effector as an additional input to the generator, so that it's kind of a conditional GAN where the configuration that it produces correspond to the target position. Next, we propose to use not a single neural network but an ensemble of neural networks, and each of the neural network will produce one configuration. So we need this because we found that the standard GAN will have problem when the output is multimodal configurations. GAN will tend to converge to one of the mode of the distribution. For example, we know that in robotics, if we are given an effector target position, there are multiple robot configurations that can achieve this target position. And if we train just one single neural network, it can converge to only one mode of the distribution. And it means that there are many other configurations that will never be produced by the generator. And in the context of motion planning, it means that a lot of time the motion planning can fail because it cannot generate samples in that area. So we propose to use an ensemble of neural networks by expecting that each of the neural network will converge to one different mode, and then we can cover more substantial portion of the configuration space. And in practice, we found that having ensemble of neural networks is very important for the motion planning. Then the third modification concerns the output of the generator. In the standard GAN, we give this configuration directly to the discriminator. But in this proposed modification, before that we perform some forward kinematics to compute some end effector positions like the foot and the hands. And then we augment the end effector position to the configurations. So this will consist of both the joint angles and the end effector positions. And then we give it to the discriminator. We do so by expecting that the position of the end effector are crucial components or crucial features that determines whether this is a good configuration or not. So we do the same with the dataset configurations. And finally, the last change is to introduce more cost function to train the generator. In the standard GAN structure, we only use the output of the discriminator to train the generator. But we know, based on our constraints, we know what good configuration means. So we can use the constraints as additional cost functions to train the generator. By doing so, the generator can learn much more effectively. Now, to show the benefit of the approach, we use GAN in two different applications. First, in inverse kinematics, we use GAN to provide initial configurations that are close to satisfying the task and also the constraints. In the second example, we use GAN to provide random samples for sampling-based constraint motion planning. So GAN is used to replace the uniform sampling. These are the configurations that are produced by GAN in inverse kinematics. So by giving the end effector targets as the yellow ball here, we show that GAN can produce configurations that are close to satisfy this task. Note that there is no optimization involved yet here, so these are pure output of the GAN. By giving the end effector trajectory, we can see that the configuration produced by GAN are quite smooth because the generator uses a smooth neural network. And finally, we can also give multiple end effector targets to GAN so that it tracks each of the targets quite well here. Now, as we mentioned before, since GAN uses an ensemble of networks as the generator, we can retrieve multimodal solutions. So given the same n effector task, we see that the configuration produced by GAN from each of the network are quite different. Look at the ARM configuration. Each of them satisfy the same task, but they are at very different configuration. And this is especially important for motion planning because it means that GAN manages to cover a substantial portion of the manifold, and this is important for the completeness guarantee. Then we use GAN in constrained motion planning. On the left here we have the motion planning for Panda arm that has to maintain vertical orientation. Then on the three examples here we have the motion planning of Talos that has to move its hand from above the table to below the table while still avoiding collision. And the environments are constructed from the most simple one to the most occluded one. And what's the advantage of using GAN as compared to random sampling? We show that it gives higher success rate because we initialize from good initial configurations. Then it can also have faster computational time, up to 5 times faster, because we require less iterations. And we can retrieve multimodal solutions very quickly. In conclusion, we have proposed GAN-based approach to learn complex robot distributions under constraints. We show that it improves the success rate and the computation time for at least 2 different applications. And since GAN is a very flexible tool, there are a lot of possible extensions that can be done. For example, because we can condition GAN on the n effector position, we can perform task-based biasing on the RRC. Or if we have the results of previous motion planning, we can also train GAN to learn from the data so that we can provide optimal sampling for new tasks, as done in this reference paper. So that's the end of the presentation. Thank you for watching.